Okay, let's practice another trapezoidal approximation used to find the approximate area under a curve over a specific interval here. And so this will be example 1, part B. Again, I purposefully gave you functions for which you could actually find the exact value, but I again will appeal to you, pretend that these functions are very difficult to integrate. But let's start with the calculus here. Exact. All right, so if we were going to integrate this one, integral, we would rewrite that as x to the 1/2 power. This is, in fact, one that we can integrate with very simple, straightforward calculus techniques. The antiderivative of this would be x to the 3/2 n plus 1, and then over 3/2 would be times 2/3. That's the antiderivative, and then followed up with the evaluate symbol, where we translate this integration over, I guess that's called the evaluate symbol. Honestly, I'm not sure, to be clear. And then you would put 7 in there for x, evaluate. So we've got 2/3 times 7 to the 3/2 power. That would be this one, minus 2/3, and then we put the 3 in there. This is that fundamental theorem of calculus, one of them that we talked about there. And then that's number crunching, isn't it? So, again, in the interest of time, I found out, crunch those numbers, it's just arithmetic, just using a calculator. 8.8827378 would be what that would crunch out to be. And that's a fairly exact. It was rounded a little bit because the decimal goes on, but that's about as exact as you can get, and that's using calculus. So that's using the more exact idea. Okay, again, if your function is easy to integrate, this is what you ought to do. It gives you the exact number, all right, or as close to exact as you can get for that area. Remember, this is the area, all right, equal to that. If you keep going, equal. Now, pretend with me once again that it's very difficult to integrate that function. So here's the picture I would like to build here. We've got our interval from 3 to 7. By the way, if you put 3 into the function, and let's identify that, wouldn't the function be square root of x? All right, so that's important to note throughout. If you take the square root of 3, it's approximately 1.73 over here. I put approximate. And the square root of 7 is approximately 2.65. And it really doesn't matter terribly how that function behaves in between there. Okay, what I'm about to draw as far as the curve there is not accurate. I'm just here to say, but it could do all sorts of peaks and valleys and everything. Woo, 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 woo. All right, that's not the graph of this one, but you don't have to graph the thing perfectly. I'm just trying to get some rough ideas in place. All right, now this one says that they want to subdivide that interval into 5 equal parts. So wouldn't the width of each of these intervals be to take the width of the entire interval, 7 minus 3, by the way, in general, that's A and B, right? Okay. And then divide by the desired number of intervals. This time they want 5 trapezoids. And I'll take you back to, again, B minus A would be the width of the entire interval. N is how many subintervals you want. This would be the width of each interval. So that is 4 over 5, which is 0.8. All right, so if we start here at 3 and keep adding 0.8, hopefully we'll have 5 subintervals. So let's keep adding 0.8. 3 plus 0.8 would be 3.8. Again, this picture is not accurate as far as the graph itself. And the idea would be that we're going to talk about this trapezoid here, these straight-edged things for which there are geometry formulas. There is a geometry formula for that trapezoid. Okay, where we've got the left edge and the right edge. And that top blue. Notice the blue doesn't match the curve, right? That's why it's called approximation, right? So there would be our first trapezoid. All right, let's add another 0.8. And this is x1, by the way. We add another 0.8. What's 3.8 plus 0.8? 4.6. That's x2 in general. And that'll give us our next trapezoid. and its left edge will be the 3.8, and its right edge will be the 4.6. And then again, across the top there, that blue trapezoid, which does not match the curve, right? That's why it's approximation. Add another 0.8, that would be 5.4. That's called x3 in this case. Notice the 5.4 is going to be, well, we got our third trapezoid. The left edge is 4.6, the right edge is 5.4. And of course, this blue, I don't know if you can see the colors that well, but anyway, there's that. Then we add another 0.8, which gets us to 6.2. Here's our fourth trapezoid, if you will. And the left edge is going to be the 5.4, f of the 5.4. And the height of the right edge of that trapezoid is the putting 6.2 into the function, where the function is square root. And there's your trapezoid there. Notice these straight edge tops of these trapezoids do not coincide with the curve. That's why this won't be exact. It'll be approximate. And then the 6.2 would be this left edge. And then if you add 0.8, we land on 7. So that should not be a coincidence. And again, there would be our fifth trapezoid. And again, its edge across the top is not going to match the curve. That's why it's called approximation. But if we apply that geometry formula for the area of the trapezoid to each one of these and do a little bit of algebra trickery and simplification, here you go again. This is how we find an approximate area under that curve, by adding up the areas of all of those trapezoids. So here we go. The area under that curve will be approximately b minus a over 2n, 7 minus 3 over 2 times 5. I always feel compelled to remind people where the 2 came from. See, each trapezoid was b minus a over n, and that would be the width. But the formula from geometry is 1/2 times that. And that 1/2 is where that 2's come from. So this is b minus a over n, the width of each one, and then the half that simply is part of the geometry formula, provided the 2 there. Okay, and then it's cookbook. F of 3. And by the way, you don't multiply that one by 2 because 3 is only involved in the first trapezoid. But all the ones in the middle, as mentioned earlier, are going to get doubled. So when it comes to the 3.8, you would hopefully agree that 3.8 needs to be doubled because 3.8 is involved in 2 trapezoids. And the reason it's being put into the function is because we want to know how tall is the trapezoid. And that's, you put it in the function, right? And that'll be doubled. And the same can be said for the f of 4.6, it gets doubled. And the f of 5.4 gets doubled. And the f of 6.2 gets doubled. I'm running out of room, sorry. But the 7, f of 7 does not get doubled. Because again, that last trapezoid, 7's only involved in that last one. I'll say it again, all these ones in the middle are involved in 2 trapezoids. It's going to be the left edge of one and the right edge of another. And that's why all the ones in the middle get doubled. I'm changing colors, green, red. I don't know if you can tell. But all those ones in the middle get doubled. Doubled, 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 doubled. But the 3 and the 7 don't. What's f? Square root. So this would be the square root of 3, this would be the square root of 3.8 times 2, the square root of 4.6 times 2, da-da-da. All right, arithmetic. Did all that arithmetic ahead of time. We're in calculus, we can handle arithmetic. That should come out to be something along the lines of 8.8774322732. And if you compare these, and I did this on purpose on your homework, I made them ones that you could easily integrate to get the exact. And if you do the approximation, they should come out reasonably close. And so there you go. So that should wrap up assignment number 29 for you guys. And as always, I'm hoping all this makes sense. And good luck to you. Everybody hang in there. Everybody doing okay? You guys take care of yourselves and your families, okay?